Is it okay if I just repeat myself one more time? Okay, so yeah, today I'm going to talk about conditional thinking. So the idea of the conditional thinking is to reflect the fact that this probability of an event A might depending on some other knowledge, such as whether or not an event B has occurred in the past. And now here is the notation for the conditional probability. So we write it as the probability of A given B. And one example in the ChatGPT is that you will have the probability of getting different answers conditional on the question that you ask. Okay. So before today, the things that we have calculated look something like this. P of A, okay? So P of one random variables. And in statistical terminologies, this is called marginal probability. And the marginal here, the word marginal, is originated from the idea or in the comparison of the joint probability. Okay, so you can see that in the joint probability here, you will have the probability and then inside the parenthesis, there are both A and the B. So that is called the joint probability. And then for this probability, you will need the associated joint probability density function or joint probability mass function to calculate the joint probability here. But when you're looking at one thing out of the things that you put in the parenthesis, then that is called a marginal. So you're only looking at one of the terms, and then we have the word marginal to describe P of one thing. So P of A is called the marginal probability. Okay. And then with the idea of the joint probability and the marginal probabilities, then we can introduce a formulation for the conditional probability. Okay, so the key formula is the following. So the conditional probability of A given B is equal to the joint probability of A and B divided by the marginal probability. Okay. And this is one key formula to obtain the conditional probability. Okay. So here on the numerator, you have the joint probability, and then you want to divide it by the marginal probability of the things that you want to conditional. So you divide it by P of the B, and then you will obtain from the joint that you have the A conditional on the B. So always make sure that you are dividing by the marginal of the B or the things that you want to get conditional on that B in this case. Okay, so this is one key formula to obtain the conditional probability. Yes?
Why is it not P of A and B times P of B? Because P of B is already less than 1, or greater than or equal to 1.
For probability, they're all between 0 and 1.
Right, so then why not multiply P of A and B by P of B? Why does it make sense?
You want to say this?
No, so keeping the order the same, keeping A as what we're actually trying to find. I'm just wondering why mathematically we put P of B in the denominator rather than multiplying by P of A and B.
I think it's never going to be more than 1 because the joint probability is always going to be less than the marginal.
By less, what do you mean by that?
Like the joint probability of A and B, that's always going to be less or equal to the probability of just B. So then if you divide like that, it'll make sure that it's going to be less than 1.
That's a good comment. Actually, I never think about that, but I'm still skeptical about the magnitude. But yes, that's a valid concern, but I'm not sure about that claim yet. But the high-level idea is that you need to keep everything between 0 and 1. That's a valid concern, but I'm not sure about how you can maintain that. Yeah. but in the context, they will need to, or as long as you have a valid probability density function or mass function, then these will all hold. Because the probability mass function, inherently, you have the constraint that you integrate equal to 1. So whether this is satisfied for these formulas, depending on, you must have a valid probability density function. But I'm not sure about the claim whether which one is bigger or smaller than, so that you can maintain that. That I'm not sure. Yeah, but that's a valid concern. Thank you for bringing that up and your comment. Yeah, thanks. Any other question, thoughts, comments on this? Yes. I'm going to post the notes, so you don't need to. Yeah. Okay, so next I'm going to talk about examples, but now let's just consolidate some of the notation. So for the conditional probability that we are going to focus in is denoted as P of A given B. So it's just like the probability of getting different answer from ChatGPT conditional on the question that you ask to ChatGPT. And then this conditional probability can be obtained from the following two components. One is called the joint probability. So we have the P of A and B, or A comma B. And then if you have multiple things, you can keep adding A comma B comma C, and then you have the joint of everything. And then when we talk about one of the things, then it's called the marginal probability. So you're only talking about one thing at a time, then you will have the P of one term. So P of A or P of B is also called the marginal probability. So these are the notation that we will be using. Okay. And then we will have this formula to obtain when you have the joint and the marginal, and then you can obtain the probability for the conditional case. Okay, so that's the notation. Now let's take a look at one example. Okay, so suppose there's a new test for a disease. And then the test has a 5% false positive rate. So here, false positives means the following. So if someone does not have the disease, there's still 5% chance that the person will be test positive. So that's why it's called false positive. Okay, so in this context, we have two things that we are concerning. One is a test, and then another thing is that a disease. Okay, and then here we claim that the test, maybe through some kind of like testing COVID, you will need some tools. So that tools or some tests have a 5% false positives. And then here, the false positives means that if someone does not have the disease. Okay? But the toolkit or that exam that you perform, you will still have a 5% chance that saying is testing positive. Okay? So it could make some error in some tests or in some toolkits to test some disease. In that case. So it's quite realistic in this case. Yeah. So we have a 5% chance of getting a false and then positive. So false is referring does not have the disease but still positive. So false positive. Okay. Now let's provide more information in this context. Okay. So one, let's assume there are no false negative. Okay, and this is referring if someone has the disease, the test will always give you a positive result. Okay, so in contrast to the previous false, what is it called? False positive, here we also claim or assume that the test has no false negative. That is saying, if the person has the disease, and then if they apply or implement the test, then the result will always return positive. So there's no false negative, okay? So false negative is saying that if the person has the disease and the test is saying will return as a negative result. So that is something that you don't want if you are inventing such a kind of toolkits to perform the test. But here we are assuming that there's no false negative, but that is saying if someone for sure has the disease, then when you implement the exam or the tools, you will have a positive results. So there's no false negative. Okay, let's provide one more information in this context. We also assume the disease is presented in 1/1000 people in the population. Okay, so here are all the information that we have in this context. So we have two things. One is the disease, and then one is a test. Okay. Maybe I'll pause a little bit for you guys to finish the notes. Or let me know if I need to scroll up. Okay. So in these examples, there are two components that we are concerned. So one is the disease and the other one is the test. And then here we also have some information regarding both the test and the disease individually. So for example, here the test we know has a 5% false positive. That is saying if the person does not have the disease, there's still 5% chance getting a positive result from the test. So quite realistic in this case. And then we then provided two more information. So here we assume that there's no false negative. That is saying the test that you develop is quite good. So that is saying if someone has a disease, then the test will always return a positive result. So that depending on some domain knowledge of some doctors who developed this tool. That means the person is doing a good job. Then if someone has a disease, the test will always tell you the truth. Okay? But in practice, in real life, that might not always happen. You might also have false negative. But here, for this example, let's assume that the doctor is doing a good job when there's a disease, and that it will always return a positive result. Okay. One last information that we know is that for every 1,000 people, there will be one person has this disease. So we use this value to define the rare disease. Okay, so here we're saying this is a test for a rare disease. Okay, so we use the number 1/1,000 to define the rarity here. Okay, so here are all the information that we have in this context. Actually, if it is 2 or 3 years ago, then this is quite aligning with what we are experiencing, and also quite realistic for some of the ideas and the setting. Any question before we proceed? Any question or thoughts, comments regarding the context here? Okay, now let me ask a question. And this question may be quite often in the clinical setting. So my question will be, if someone is test positive, what is the probability that they have the disease? So I would say this is also a quite valid question to ask. Because you don't know whether you have the disease or not, that's the starting point where you want to implement the test or go to the doctor to ask for an examination. So now, let's say after you implement the test and the test returns a positive result, now I'm asking what is the probability that the person has the disease? That is also a quite realistic and valid question to ask. Okay, so now based on the context that we have two components, disease and a test. Here I also have a question regarding disease and a test. So any thoughts on how we should, yeah?
Well, you like define your variables, like
Mm-hmm.
and a variable for whether they're infected and whether they tested positive.
Mm-hmm. And then?
And then you have like probability of being infected given a positive test.
Using the formula that we have seen to obtain some information like that, right? Is that what you're saying?
Yeah, or you can like make a table.
Good. Thanks. Yeah, that is what we are going to do. Yeah. Yeah.
So we set up the equation of A given B,
Mm-hmm.
and then we have to calculate the probability of positive tests, P of B, because that is based on
The one you want the conditional on, right?
Yeah, but I don't think you have to treat it as another conditional. It's just adding separate probabilities because I think they're independent.
Sure. We will talk about some details after that. But the high level idea is that you guys were agreeing on using the formula that we have seen to get the conditional conditional property, right? Yeah. So that is the high level strategy that we're going to do. And next, throughout the process, I'm going to introduce some more formulas to obtain or to handling this kind of the probability with the conditional thinking here. Okay. Yeah. Thanks for the answer. Yeah. Any other question, comments, or any discussion here? We have the context, we have a question. We also have a high-level strategy on how we should handle this. Let's see if we are able to do that. Any other thoughts regarding the context here? Okay, if not, then let's proceed with our strategy on handling this problem. Okay, so maybe now let's first providing some letters or notation just to ease our notation in the mathematical formula. So maybe let's call the disease as the letter D. Okay, so let me give a like a capital letter D for the disease or having the disease. Okay, and maybe let me also give a symbol for positive. So testing positive. Okay, so where should I put this? Positive. Okay, so maybe let me put it here. So I'm going to call the case for positive as like a plus with a circle. Okay, so that is the result from the test. Okay, so now I'm just introducing two letters. So if you have a disease, I'll put a letter D, and then if it's testing positive, I'll just use a plus sign. Okay, so once we have defined these two components, let's go back to the question here. So we're interested in the probability that, so in the mathematical language, is the following. The probability of having the disease, so P of D, but given that the test is positive, so we want to conditional on the plus sign. Okay, or you can use other letter to denote, but now I'm just going to use a plus, like an icon to define that. So, based on the question, in mathematical language, this is something that we are interested in. The probability of disease conditional on the results positive. Okay, but now we convert the text or the question into mathematical language, and then we are ready to apply the formula. So earlier we have seen that the conditional probability is equal to the joint, which is the D and the plus sign divided by the things that you want to conditional on. So in our case, we are going to conditional on the probability of testing positive. So we want to conditional on the probability on the plus. Okay. So what I've done so far is that based on the context and then also based on the question, we come up with the term on the left-hand side of interest. And then applying the formula that we just introduced earlier, we have the joint divided by the marginal, divided by the things that you want to conditional on. Okay. So now we have a formula that means as long as we have the formula or the numbers for the right-hand side, we'll be able to calculate the probability of interest here. Okay. So my next question would be, do we have the probability or the information on the right-hand side so far? Do we know about what is the probability of the joint here, or do we know about the probability of happening or only testing positive? Yeah.
I think we have the information for both.
I mean, just based on here, on all the context, we have both. Okay. Then what would be the probability of the joint here?
The probability of the joint is assuming that getting a positive test and having disease are independent. So disease is 1/1,000. And
Okay. Uh-huh.
is it 1/, 1 times 10 to the power negative 5 instead?
You bring up a very interesting topic, which is called independent, right? However, in this case, they are not strictly speaking independent. So that is the key difference of the conditional thinking. So here, instead of independent, something that are not related, like rolling 2 dice, the outcome for the first dice is not going to affect on the second dice. Here, the things are no longer independent. They are conditional on each other. So you might have the disease and then you test positive, or yeah.
Is this where you have to flip the question and the answer because we know the value for the
Perform some manipulation on the formula, right? Is that what you're
Yeah.
saying? Yes. So that would be the idea here. Yeah. Yeah. So you bring up a very important concept which is called independence. So in the idea or in the regime of the conditional probability or conditional thinking, it depends on the knowledge. So rolling the first dice is not going to affect your result on the second dice. But in the idea or in the regime of the conditional thinking, things is going to depending on each other. The answer that the ChatGPT going to generate is going to depend on your question. So they are not independent. It's not like you're asking a question to ChatGPT, but ChatGPT answering totally irrelevant things, right? So it's going to depending on that. So the idea or the concept of independency no longer works. Yeah. So this is also what I was saying earlier. This is more aligning to human intelligence or human behavior. We are always depending on the past to come up with a decision nowadays, or today. Right? Yeah. So the independency, all those concepts, no longer applicable in this context. But you also bring up the idea that we want to manipulate the formula, maybe flipping something, the orders, or later we'll see how we do that to obtain that. So that will be the next steps. Okay, so now let's take a look at what information that we actually have. Okay. So let's take a look at the first piece of information that we can collect from the prompts or from the question here. So we know that the test has a 5% false positive. So that is saying the person does not have the disease, but there's still a 5% chance to test positive. So let's write that down in terms of mathematical language. So the first piece of information that we can get is the following, is the probability of testing positive, right? Conditional on the person. So let me put ND for there's no disease, okay? So the probability of testing positive, conditional on the person does not have the disease, okay? So let me write it as plus conditional on ND. Let me just go back here. So the person does not have the disease, but still testing positive. So P of the plus, conditional on does not have the disease, has a 5% chance. So that is the first information that we have here. So the first piece of information is the P of the plus, conditional on ND in terms of mathematical language, and no disease is equal to 0.05. So that's the first information that we collect from the question. Okay. Now let's take a look at what are some other or second piece of information that we can get here. So here we said that there's no false negative. So that means if someone has the disease, they will always test positive. Okay? Let's write that down in mathematical language. So the second piece of information is the probability of plus conditional on having the disease. This is equal to 1 or 100%. So let's assume the doctor is doing a great job. Whenever you have a disease, the exam will always give you a positive, and that is always true. But in practice, the doctor may also make a mistake. So even if you have the disease, the doctor may tell you that you don't, or the test is not going to give you a positive result. So that's giving you an error. Okay, but now let's assume it's 100%. Okay. Also, just to clarify, the things that we are really interested in is the probability of disease after having a test. So this is what we are doing when we testing COVID. You're just implementing that toolkit, and then it will return you the test. But the question to you is that whether you really have the disease or not. It might test positive, but you don't have the disease. So we are interested in this one. But the information that we have from the question or that we can collect is the other way around. Is that the probability of having a disease and then it gives you the result positive is 100%, which means the doctor doing a good job or the test is great, is always correct, and that is the information that we have. Okay. And we also have the third piece of information here is that if someone assume the disease is present in 1 over 1,000 people in population. Okay, so for this one, rewriting this in the mathematical language is the P of the D. This is only involving the information or the component of having a disease or not. So we can write this in terms of a marginal probability, the P of the disease in the population. We're not talking about whether the test is positive, negative, doing good or doing bad. We're only talking about the disease. So P of the disease as a marginal probability is equal to 1 over 1,000. And we use this number to define the rarity thing. Okay? This is a test for the rare disease. Okay, so now based on the question, we rewrite the information into mathematical language. Are we able to obtain the right-hand side? A question?
Yeah, for the joint probabilities in general, does it matter what level you put them in?
Oh, sorry, can you say it again?
For the joint probabilities on the right side, does it matter which order if you put
It doesn't matter.
disease or
Yeah,
positive?
it doesn't matter. Okay, so on top, this is the quantity of interest. We know we have a formula. We can write it on the right-hand side in that way. Also, these are the information that we have collected. So for example, you can run some clinical trials and ask 1,000 people in taking the trial or taking the test, and then, that's not a good example, but here you can collecting these information from the data by performing some experiments or clinical trials. Yeah. So these are the information that we have. Then my subsequent question is that do we have information to handle the right-hand side or not? Okay, just by directly looking at that, we don't have anything about the numerator and the denominator because any of the latter does not match. The marginal we have is the P of D. The conditional is that, yeah. So none of these quantities that we collect from the date question.
But I guess you could make a little table to fill in the blanks based on what you know, right?
Yeah, that would be one way to do it. Yeah. You mean fill in the table for the probabilities? The thing, okay. Sure. Yeah, that would be also one way to do it. Yeah. But maybe let me just applying formulas and then to write it more of a, I don't want to say rigorously, but through step-by-step thing instead of like a table. Yeah. Okay, so we have the things that we want to solve on the right-hand side. These are the information. Let's see, question?
I had a question was about the joint probability. Do you eventually have to multiply like the probability of 3 and 2 together or no? Or something like that?
That's a good question. Let's take a look. Okay.
I think I might have missed it.
Yes. So one thing we can do here is that we have a formula to handle a marginal, a conditional, and then a joint. So now on the right-hand side, you'll notice that there's another joint here, right? You were saying there's a joint. So can we apply the same formula to this or not? Is that what you're asking?
Yeah.
And the answer is yes. We're going to apply the formula again on the numerator only to obtain the probability. So again, this is the quantity of interest. Applying the formula for the first time, we obtain the right-hand side. Okay? So this is what we have. Applying for the first time, we obtain the right-hand side. But we notice that neither of the information can be directly input to the terms on the right-hand side. That means we need to apply the formula for the second time, okay? So more specifically, maybe let me put it here. So now let's take a look at the numerator. So the numerator is the P of the D and the plus sign. So this is the numerator, which is the joint. Okay, now let's apply the formula for the second time. And we are going to use the following information. So we're going to use the conditional multiplying by the marginal. So our first time when we use the formula here is that we do the conditional is equal to the joint divided by the marginal. We can also rearrange the term to obtain that. Maybe I can put it here. Let me rewrite another version of this one. Okay, so the formula here is also saying the joint is also equal to the conditional multiplying by the marginal. So these are exactly the same formula. I'm just rearranging the order. So the formula is So the formula is that the conditional is equal to the joint divided by the marginal. But when you move around the terms here, the same formula also gives you the joint is equal to the conditional multiplied by the marginal. And the second formula here is the one that we are going to use in our second terms here. So again, the joint is equal to the conditional multiplied by the marginal. Now let's take a look at this numerator. On the numerator, we have another joint. Then applying this formula again for the second time, we're going to write the joint is equal to the conditional multiplied by the marginal. And this time, these terms and these terms, we can see that we do have those numbers from the information that we collected here. That means we have a way to handle the numerator. So now let's plug in the number. The probability of plus given the disease, we know the doctor is doing a good job, so it's equal to 1. Multiplying by the probability of the disease in the population is 1 over 1,000. So we have the probability for the numerator. Okay, so you can see that after you apply the formula for the second times, you'll be able to obtain some results. And in this case, we have the joint equal to the conditional multiplied by the probability, by the marginal. Okay, so we have handled the numerator. Now let me also introduce another formula just by giving a name of what we have done here. So this is called the Bayesian theorem, and then in the generic letters, this is the following. So B, the probability of B conditional on A is equal to the probability of A conditional on B multiplying by the probability of the B divided by the marginal of A. And this is called the Bayes theorem. So the high level idea is that when you are interested in the probability of B given A, one thing you can do is to reverse the order as the probability of A given B, but multiplying by the marginal or by the things that you're conditioned on. So from the earlier example, we notice that the thing on the numerator is just by applying the formula for 2 times. Then you will obtain this formula here. And this formula has a name, it's called the Bayes theorem. And it allows you to handle the probability by reversing the order of the events. Question?
Do you assume that A occurs before B or B occurs before A?
It doesn't matter. It just, so if you want to say what happened in the future given on the past, this is saying if you know what happened in the past, you can kind of reverse the order. So the formula giving you the power to doing the reverse order. Like what is the probability of a past given the future? But if you want to calculate that, you need to know what is the probability of future given the past. You need to have 3 of them first to get the counterintuitive part, the future given the past given the future. Yeah. But the high level idea is that it allows you to change the order. Yeah.
Wait, so is the output the past and the input the future, or?
It doesn't matter. It depends on how you define A and B. So if you define B as your past, then this is saying past given the future. But then that means you also need to know what is the future given the past. By just giving you the power to switch the order.
So can it like gives us like flexibility either one or?
Sorry, can you say that again?
So does it gives us like the freedom to pick either one or like to fit?
Yes, you can always use the formula, but you need to have those information first, right?
Yeah.
Yeah, but if you don't have the information of the future given the past or the past given the future, then this formula, you cannot apply them, right? Or maybe I misunderstand your question.
No, it's just like
Yeah, you can always change the order. Yeah.
yeah.
So this formula give you the power to change. You can change the order. Yeah. Like what is the probability of the past given the future? Yeah. Or the other way around. Yeah.
Now that we've covered this, could we revisit why we divide by probability of the question?
You mean in terms?
P of A in this case, probability of A.
You mean the reason?
Yeah, because we did for the joint probability, we did multiply by the probability, like given the conditional of one based on the other, multiplied by the probability of the condition occurring, right? That gave us the joint probabilities. So then, what does it mean to divide by probability?
I see. So I would say the idea of dividing a probability is that you are only focusing on that events. So let me find a good way to answer that intuitively. Okay, so for example, here we have the idea of testing positive in the denominator. So in this case is that when we lock down on the events, when after we implement the test and then it give us the positive results. So you can consider that when you divide it by that is saying that we're only focusing on that events. We lock down on that events. When we lock down on that events, then we interested another quantity, which is whether we have the disease or not. So when we lock down on, we already know the test is going to be positive. Then what is the probability of having a disease? So the division, by dividing that marginal probability, is saying that we're focusing on the case when we only looking at when we already know the positive result. The test is giving you positive. After you lock down on that scenarios, you want to consider or discuss the second component, which where you have the disease or you might not have the disease. But narrowing down on that scenario, on one scenario first, talking about the probability of the second term or the second scenario, which is having disease or not disease. So this could also be. So the division here is kind of like you lock down that scenario. And so that is the intuitive answer for that. The mathematical answer for that is that you need to scale by the probability here to make it, everything will sum up to 1. Okay. So this is saying the probability of A given B plus the probability of not A given B need to sum up to 1. So for this one, to sum up to 1 or to make these are between, I think back to earlier, you were saying to between 0 and 1, the thing, so mathematically is that you need to divide it by the probability that you're narrowing down, and then the probability of having disease or not disease will be shrink or scaled by the corresponding component, when you sum them together, this will need to be 1. So from the mathematical standpoint is that you want to scaling things to make it, they were still between 0 and 1. But for intuitive answer is that you want to lock down on one scenario on testing positive, and then you can discuss the component on the second scenario, having disease or no disease. Yeah, that's the intuitive answer for that. Yeah. Yeah. Okay, so maybe let me just providing the full. So here we are interested in B given A. By applying the formula for the first time, we know this is the joint over by the marginal, which is the joint divided by the marginal. The thing we want to lock down, the scenario we want to lock down. When we apply for the second time, then we have the A given B multiplied by PB. So this is applying the second time on the numerator. We obtain the formula, what we call as the Bayes theorem. Yeah. So this is how we get that. Applying the formula on the numerator only for the second time, we will obtain that formula, and that is called the Bayes theorem. Okay. And then by using that, we have a way to handle the numerator. So the next question is that, so now we're having the numerator. Now the question is that how we handle the denominator. So the denominator is saying only focusing on the test. So whether the test is going to be positive or negative, regardless of whether you have disease or not. So the question now, how to handle the probability of the marginal of the getting a positive result. Any question or comment? Yeah.
Could you, if you're assuming it independent of disease, would you do 50-50? Would you assume 50-50 since there's 2 results, and then you consider the probability? Sorry, you just assume that what it is dependent on is it's 1 over the number of outcomes.
Yeah, so first of all, the independency may not imply that it's 50-50. You can also have 2 independent coins, but the probability of landing on head and tail is 0.3 and 0.7. So independency is different from the probability. The probability only depending on the probability density function or the probability mass function. And the independence is more of a high-level condition for the 2 coins. Yeah, but the individual coins, they're probably depending on the probability density function. Yeah. So in this case, we will need some additional tools to handling the marginal probability for having a test. And let me define the new idea here. So the new idea or the new formula here is called the law of total probability. Okay, so the idea of the law of the total probability is the following. So let me use generic letter. So P of A is equal to the probability of A and the B plus the A and the B. Maybe let me use mathematical notation. So B complement. Okay, so I will add the C on the top. So this is for the complement. This is also saying not B. Okay, so that is the idea of the law of the total probability. We can also provide a visualization in the Venn diagram to observe this one. So for example, we have the circle for probability for events A, and then we also have a probability or a circle for the event B. Let me color this region in red. Let me also color this region in black. Okay, so the probability for the joint of A and B is represented by when the two events happen or occur at the same time. So you will have the black region when they overlap in this visualization, in this circle. Okay, so the probability of A and B happen at the same time is the region where they overlap, so which is this part, and I'm just dragging this part into here, which is representing the region of the first part. And the second part is referring that the probability of A, but without when the B is not happening. So the B happening is represented by this circle, but the B not happening is represented by the outside this circle. So whenever it's outside the circle of the B, but also when A happens, it's actually the region in red. So the second component is actually this part by removing the common region. Okay, and that gives you the law of the total probability. So the marginal, the P of A, which is represented by the circle of A only, you can see that when depending on some of the other events, then you can separate the circle of A by two regions, the black region and the red region. And the black region is referring that when both A and B are happening at the same time, so that's the black region. And when B is not happening, or B not B, that means the region outside the circle of the B, but is still A happening, will be the red region, and this is this part, and then it is equal to the left-hand side. So this is the whole circle for the A with the black part, and then also the red region. Okay. So A happening is only the circle of the A, and B happening is only the circle of the B, and B not happening is the region outside the circle of B, but still A happening, so that's the region A, but not overlapping with the B, so you have this chunk here. And then when you combine the two chunks together, you will obtain the original circle. And that is the idea of the law of total probability. Yes? Oh, yeah. Here? Yeah. This is, I'm just repeating repeating myself, but what happened. Any question, comments? Okay, so now let's using the idea of the total probability, let's see if we are able to obtain the denominator. So P of the plus, using that, is equal to P of the plus and disease plus P of the plus, no disease. So although we are narrowing down on this situation, this scenario, we can still calculating the part that we narrowed down, focusing on by introducing the D and the non-happening, no disease. So we're introducing additional component, but you need to sum them together, just like the circle and the elliptical shape, to obtain the full circle of the thing that you want to narrow down. Okay. However, we are now encountering two more joint probability, and based on
I'm sorry.
you go yeah.
The thing of thinking of this one, we don't have to we don't have to use Bayes' theorem or do the full equation for this one.
Yeah.
We were already given information to just.
We can just use the formula again, right?
Yeah.
So now based on this, the law of the total probability, we encounter two more joint probability. But again, we have a way to handle the joint probability. That means we use the formula for the third time to calculating those two joint. Yeah, question?
So here you don't need to use any conditional probabilities?
Not yet, yeah. So now I'm going to calculating the two joint using the condition. So what I mean is the following. So this is equal to the probability of the testing positive multiplying, given having a disease, multiplying by the probability of having a disease, plus the probability of testing positive but no disease, multiplying by the probability of no disease. Okay, so this is applying the formula for the third time on two joint. So the formula that we have giving us a way to handling joint, marginal, and conditional probability. Now we encounter two more joint, and that it tells us we need to use the formula again, which is applying the same thing for the third time to handling the two joint, rewriting in terms of the condition. Okay, so we're just applying the formula for the third time. Okay, then we come up with this formula. The question is that whether we have the information for these four terms. Otherwise, the formula is useless, right? So after we apply the formula for the third time, we come up with these four terms. Do we have those information? Let's take a look. So earlier, we have these three pieces of information. So the first, the 1 and 2, is the probability of testing positive and no disease. And the other one is testing positive and having a disease. So let's see. Can we plug in the number here? Plus and ND and plus ND. So based on the information that we write down earlier, we have this one, we have this one. Okay. Then we have two more terms to concern. The probability of having a disease and the probability of no disease in the population. Let's take a look again. Okay, we have seen that the third term is exactly the probability of having a disease. So this term is also taken care of. What about the probability of having no disease? How do we handle that? Yes. Yes, exactly. So we know the probability in the population, there's 1 over 1,000 probability of having. That means 1 minus the having disease, then it would be the probability of having no disease. So if you want, you can rewrite this part. So plus the probability of tests giving non-disease multiplying by 1 minus the probability of that. You have this, you have this, you have this, you have this, then everything is covered. Okay, so you can see that when we applying the formula for the first time, we have a way to change the order, or 2 times we have the way to change the order. And we have a very specific name for that. It's called Bayes' theorem. When we apply for the third time, we'll be able to handle the law of the total probability. And now, everything on your right-hand side, after you expanding or replacing the terms, you have the information for everything. And then we can plug in the number to calculating that. Okay, so now let's plug in the number. So P of testing positive is equal to positive giving disease. What number is that? Plus giving disease is 1. Okay. So that means the test is doing a good job. You always give you the positive result, multiplying by the probability of having the disease in the population. So 1 over 1,000. And then plus the false negative. So this is the error the test is making. You have 5% chance when the person does not have a disease, but is still going to give you the positive. So P of the plus given no disease is the error is 0.05. Multiplying by 1 minus 1 over 1,000. Yeah. So that 1 minus 1,000 is like the probability of today is raining is 0.0 is 30%. Then the probability of not raining is 1 minus the probability of raining is 1 minus 0.3, you'll get 0.7. 70% for raining today, not raining today or something. Okay, so that's the denominator, and then we also have the numerator. So back to our question, probability, whether you have the disease after you observe a positive test result, is the numerator 1 over 1,000. Divided by the denominator, which is that number. Do I have that number? Okay. So P of the, let me just do that. So I think the number that I have is 0.0196. Okay, so that is the probability of the disease. So during the COVID, you probably do the test yourself. If you obtain the test is positive or negative, the question is whether you really have the disease or not. So in our case, the probability is 0.0196. Let me just ask an intuitive question. Is this probability large or small? Small, right? Okay. So let me just revisit the problem here. So here, even if the doctor or the clinical person developing this test having no false negative, that is saying that the tools or the exam that this doctor developed is very strong, very good. When you have the disease, you always test this disease. You always test positive. But you can see that the probability that you have a positive result. Now I'm asking whether you really have the disease or not. It can be very, very small. So even if the doctor invented the most powerful tool, like 100% when you have the disease and then test positive, the probability of having the disease, once you know your result is positive, it can still be very small. So the idea of the conditional thinking is very intricate here. So even your tool is powerful, your tool is giving you positive. But I'm asking whether you have disease or not, it can still be very small. So you can still not determine whether you actually have the disease or not. So the diagnosis here can be very difficult. And let me ask a follow-up question here. Why this is happening here? A question or comments?
Because even though it's so accurate, it's accurate in a very small percentage of total cases, 1%, and then it has a 5% inaccuracy in every other case, which is 99% of the cases. So that leads to that significant inaccuracy is a greater concern because that happens far more.
Yeah, that would be the high-level idea. Yeah, and actually, that we have one word that we use to describe what you're saying. This is a rare disease. So even if you have a very powerful tool for a rare disease, 100% true. When I know you have a disease when I test, 100% give you positive, even for rare disease. But the probability when you receive a positive result, you still don't know whether you have the disease or not. Yeah. So even if you know you're positive, you still might not have the disease actually. Okay. So well, we only have 10 minutes. And maybe I'll just stop here. Is there any question, comments, thoughts? Yeah.
Would this test then still be useful if there was a secondary diagnostic method
you need to conditional on more. Condition A conditional on B and C, and then keep doing it, or A, B conditional on C, something like that.
What if it was like an independent diagnostic test for a different?
Then you have the A conditional on B and C conditional on D, and then multiply them together.
There.